Okay, so good morning, everyone. So for this last lecture, we will finish discussing a bit correlation and entanglement that I intended to doing on Friday evening. And then we will go to introducing fermions, and especially, let's say, superexchange and magnetism. But before that, someone asked me a question on Friday, and I was about light-assisted collision, so I don't know who it was, but I wanted to give a reference, so you can look, for instance, in this reference here. And what I told you last time was that if you are, if you shine some near resonant light to cool down the gas, then you have a chance that one atom is being excited, and then in this S plus P channel, atoms are getting accelerated. So they gain some energy before, let's say, going back to the SS channel. And if this difference in energy that the atoms have acquired is larger than the typical trap depth, then you lose them. So that's the idea behind these light-assisted collisions. Okay, so please look at this reference. It's relatively, I mean, it's well explained, and it's exactly about discussing this effect. Great. So let's go back to what the question I raised last time. What about many-body correlations and entanglement close to this bosonic Mod transition? And so I don't have, of course, I mean, this is a really complicated topic, and there are many ongoing works, both on the experimental and theoretical side. I mean, as you know, it's not that we have a well-defined and clear definition of what is many-body entanglement. I mean, in a system of many particles which are interacting. There is one aspect which is now relatively clear, at least on some Hamiltonians. So once again, this is not a universal statement. But you can have a look at this recent paper here from Ferry colleague, is that if we are interested, so this is like a kind of a phase diagram, temperature on the vertical axis and the controlled parameter on the horizontal axis. So in the case of the Mod transition, this small j is the ratio on-site interaction U divided by tunneling j. And what is now relatively clear for many Hamiltonian is that if you want to study the quantum phase transition, so the one at t equals 0, which you don't have in the lab, there's still a region at finite temperature, which is called the quantum critical region, where the scaling of order parameter or certain quantities, thermodynamical quantities, for instance, with the temperature as exponents, which are the same ones that you would get at 0 temperature, which means you can still be looking at, let's say, this finite temperature physics. But of course, I mean, this has to be relatively low temperature in order to get information about what happens really as strictly speaking t equals 0. Once again, this is not a general statement. I mean, it depends on the type of Hamiltonian and so on. But still, I mean, I think it's nice to have these ideas in mind, which are interesting also because, I mean, they may apply to experiments.
Very good question. Do you show that there are Hamiltonians that do not have this property?
Sorry?
Have we shown that there are Hamiltonians that do not have this property in the quantum physics?
Not that I'm aware of. But actually, the type of Hamiltonian, for instance, that they are, let's say, studying in this paper are, let's say, I think it's mostly Ising Hamiltonians. And so I don't know how much it has been, let's say, applied to many of other Hamiltonians. You know, I'm not a theorist, and what I get from this message is, well, look, I mean, even at finite temperature, this I know I have in the experiment. There are interesting things to measure and to study. Okay, so let me just tell you a few words about the Mod transition for bosons that we were talking about. Wow. Go fast. Okay. So one person raised the question about critical exponents. So let me mention two experiments. One performed in Chicago, where they were studying this transition from a, so you recognize the phase diagram at finite temperature. This is temperature, and this is on-site interaction to tunneling. So a Mod insulator at t equals 0, a superfluid here, some kind of region where the Mod is melting, and then this superfluid to normal transition. So in the group of Chicago, they were able to measure the in situ density and study somehow the equation of state from this measurement. And they could recover how the critical temperature evolves with the local chemical potential. And so this is a measurement where on the many measurements, they were extracting this nu exponent and this zeta exponent. And you see that the region they get is in good agreement with what is predicted theoretically. So of course, I mean, there's quite of spreading, but still, that was, I think, a really nice experiment from this point of view. In my lab, we recently looked at this, let's say, mod transition, or rather crossover, from the superfluid to the mod region. And what we have been looking at is, so it's in 3D, we have been looking at the condensed fraction, and this condensed fraction is supposed to scale as 1 minus, so small u here, it's the ratio u over j. And it's supposed to scale with this 2 times beta exponent. And the 3D mod transition should be in this university class of the 3D XY model, so beta should be that one. While if you take a mean field treatment, you get 0.5. And you have here this condensed fraction plotted as a function of 1 minus u over uc. And you see, so these experimental dots, they kind of follow what are the squares, which are quantum Monte Carlo calculation for a trap system, and deviate from the mean field value. So it looks like you get some traits of criticality, even though you are at finite temperature and you have a trap. So one of the intuition here is because in the trap, the Bose-Einstein condensation appears at the center of the trap, where the trap, it's a harmonic trap, so where the trap is flatter. And so this most probably helps to get this type of results. Okay, so we can access some measurements of these critical exponents in experiments. So now, what about correlations and, wow, let me do like that, and entanglement. So there was this, I would like to mention this beautiful experiment which was performed 6 years ago now at Harvard, where they measure one type of entanglement. So let me tell you how it works. So these are pictures from their paper, and it's really crystal clear. So they are considering a one-dimensional gas of bosons on a lattice. So that's why you have these black dots here. They represent the atom on each side of a lattice. And the question is the following. The type of entanglement they are measuring, it's related to what type of entanglement exists between two partitions of your system. So you have the initial system, which is all this, or all that. Okay. And if you have a product state, so that you can divide your system in two parts, and write the total wave function as the product of two pure states. What happens, of course, is that if you would trace out over all these B parts, what you will end up is to have a pure state, of course. If you would have some kind of entangled state in this degree of freedom, so the spatial position of the atoms there in this lattice, so represented by those different arrows, if you cut the system with in the same way, what you will end up by tracing out of the subsystem B is a statistical mixture, right? Just because you are removing, let's say, correlations which are located between the two partitions. So this is the type of entanglement that they did, trying to look at entanglement when you partition the system. So this is done with a quantum gas microscope. What they were doing to measure this type of entanglement was to measure the purity of the system in the following way. So you have, it was a 4-site one-dimensional system. So the fact that it's rather small is because actually it's extremely difficult experimentally to get everything, let's say, perfectly, working perfectly in order to get this purity, this measurement of purity. So you make two identical copies on those two lines. So here they are not coupled, okay? Two identical copies. And then what you do is you remove the tunneling along the one-dimensional direction of your system and let the atom tunnel in the transverse direction. But for a given time, the time for which you do a Mandel experiment. So you may know this Mandel experiment. You send two photons on a beam splitter. Sorry. No? Where I should send them. And no. So let me try. I will try to send one like that and to send one like that. Is this better? So you may have situation 1 and you may have situation 2. If the two photons are identical, right? If you cannot distinguish them, they are in the same spatial and temporal mode. Then you have these interferences on the sorry, it's a 50-50 beam splitter. And the two photons will always go on the output together. So either that direction or either there, but you will never get 1-1. Okay? It's Mandel. So what they are doing is the same. They let the atom tunnel here along this one direction for a time that corresponds to creating a 50-50 beam splitter. And then what it means is that if the two atoms are kind of in a pure state, they will end up either both up or either both down. Okay? And if they are not, you may have one up, one down. So it's a way to measure purity in the same way you would do it for Mandel, except that now they are doing it like with 4 atoms in a row. So this is the general idea. I'm not entering the details. But from this type of, let's say, kind of purity measurement, they can extract this Rayleigh entropy. So it's, the definition is there. So the n-order Rayleigh entropy is defined here. So the Rayleigh entropy is typically the power n of your reduced density matrix, right? The one I get when I trace out on the part B. Yes?
How did they realize this? So are these like two independent lattice?
Yes.
And then they just run them?
Yes. And of course, I mean, they studied, well, how you should proceed in order to get a 50-50 beam splitter. I'm skipping all this, but this is actually the really tricky part. And they showed that, yes, indeed, I mean, if you, typically they looked at, well, whatever. They showed that for just like two lattice sites, they could really get 0 probability to have one atom in one direction and one in the other one if they would prepare it in a pure state. So, well, these are, let's say, experimental details. Important to get the measurement, but I don't have time to discuss them here. So this type of entropy, it's one way to, let's say, characterize some power of a reduced density matrix. Okay? And so from this purity measurement, they could measure this second order Rayleigh entropy. And now it is plotted as a function of u over j, so the usual parameter driving the mod transition. So this part here, it's in the mod state on the left hand side. And here it's in the superfluid state. So the mod transition here, it's in 1D, it's around 3 something. So you see it's around this region here. So what they obtain is that in the mod, it looks like a pure state, which is what we expect, right? You remember we said that the mod state is a Fock state on each lattice site, independent from one another. So in such a measurement, you should get indeed a pure state. While in the superfluid, you have some entanglement that grows. Okay. The one thing I would like to tell you, to remind you, is that this is one way of defining entanglement, but you can think in many ways, right? It depends on the degree of freedom you are interested in. And what happens often, at least in, once again, in Ising-like system, is that if you would plot, let's say this is some type of degree of entanglement, as a inverse, as a function of the driving parameter, what you get is an increase of entanglement at the quantum phase transition. And this somehow, at least my intuitive picture, is that you have a quantum phase transition from one state from another, and when the system has to, so far from one direction, it's a given state, far from the other one, it's another state, but close to the phase transition, in the critical regime, the state has to adapt and to change from one state to the other. And the way it does that, of course, is by creating correlations between the different particles in order to change the many-body wave function. So once again, this has been, so I really like this paper. Well, sorry, it's not written, so it's 2002 paper. And I think it's nice to read that to get some ideas. I mean, once again, we don't have any universal statements on any type of Hamiltonians and so on, but this is really interesting ongoing research. Okay, so now, well, I was talking about many-body correlation and entanglement, and I would like to give you one reason why here, so we are talking about superfluid state, you have some entanglement. Because, I mean, if you think about what Michael has said, if you have a pure BEC is a coherent state. And if you ask any person from quantum optics, what is the entanglement in a coherent state, the answer would be 0, right? There's nothing interesting. So why is there some entanglement here? It's because you have interactions. So it's not just a coherent state. And I would like to tell you about how you can see from Bogolyubov picture that you have seen with Michael, how you can see that entanglement is, let's say, arising from the presence of interactions. So let's consider a weakly interacting Bose gas. I will take T equals 0 and treat it with Bogolyubov. So you know that, let's say, if I would say that the gas is non-interacting, then the ground state is the pure BEC, right? Just this coherent state. While if you have interactions which are non-zero, then you have the quantum depletion which is present. So now the ground state, it's some kind of superposition of the BEC plus, well, I'm writing things a bit, plus some k minus k pairs with some coefficient vk over uk, and, well, so the details are not that important, but what you have is, as a function, as a result of interaction in quantum fluctuations, out of a BEC you have particles, I mean, components of a Modi wave function, which are k minus k correlated. Right? You've seen that in last week. Okay. So this is okay. And so the question I would like to raise is, what do these pairs give as a property related to entanglement to the ground state? So of course, I mean, the presence of these k minus k pairs are new type of correlations which exist in the ground state, but are not there at u equals 0. So to answer this question, let me first tell you how we can quantify the presence of those pairs, and then we will see, so through correlations, and then we will see what type of information it provides us with. So because we are talking about pairs of two atoms, to characterize it, you want to look at two-body correlations. And of course, because those pairs are in momentum space, we will look at two-body correlations in the momentum space. So something like a dagger k prime, a dagger k, ak prime, ak. Okay, this is just the two-body correlator in the momentum space. And now I will use a fact that I guess you have also seen last week, is that Bogolyubov is Gaussian theory, like any state of a Bogolyubov model is Gaussian. Right? This is because the Hamiltonian is diagonal in the quasi-particle basis. So in the quasi-particle basis, any, let's say, density matrix would write as an exponential of something which is quadratic, which in terms of operators, which means it's a Gaussian. well, Gaussian in quasi-particle basis, and then the linear, you have a linear transformation from quasi-particle to particle, so it's also Gaussian in particle. So the theory is Gaussian, and so therefore I can use Wick's theorem, which allows me to develop this guy. So I have all the three type of two operator products that I can construct. So I have this one. I have this one, A dagger K, A K prime. And I have this one, A dagger K prime, A dagger K, A K prime, A K. Okay, I built the three terms that corresponds to the different products of two operators. So this is Wick's theorem. So let me, well, I will call, well, no, I will write directly here. So what is this first term? This is the density, momentum density at K prime. This is the density at K. This guy is emission conjugate of this one. So you see that this is nothing but the modulus square of a G1 function, Kk prime. I mean, this is the G1 function. Well, times the this is normalized, so let me just write A dagger K prime AK for the moment. And we have a last term, which is also it's modulus square of A dagger K prime A dagger K. So if now I want to look at the, as people are doing in quantum optics, some normalized correlation function, so the two-body one here, I normalized it. So I normalize this two-body correlator by the product of the two densities. What do I get? The first term is 1. Okay, because I've just normalized it. The second one, it's what I had written before. It's the normalized one-body correlation. So G1 of Kk prime, modulus square. So this is the second term. And the last term, well, I will keep it like that. A dagger K prime, A dagger K, modulus square. So I have those three terms because of a Wick decomposition. And now you may recognize so if I have no interactions, I have this type of term, right? And this is actually something that you can get just with a classical field. I mean, if you would treat, so this, well, this is what gives you the bosonic bunching. Right? It's a bunching term. When K equals K prime, then you have a 1 here, and you get a factor 2 for the bunching when you look at local. And so this is only coming from statistical properties. The fact that we have bosons. While this term, so these guys are called normal correlation. While this term here may be only non-zero only if you look at k primes equal minus k, because you have those pairs. So this is associated to these atom pairs, k minus k. And so therefore this type of signal is the one which is related to the fact that you have put interaction between the bosons. While this one you have it even without interactions. And so these correlations are called anomalous correlation just because they don't conserve, you know, it's a A-dagger operator. And of course, I mean, if you would have a thermal state at equilibrium, I mean, this type of operators are zero. Okay, so you see that what Bogolyubov tells us is that in terms of correlations, you have a new type of correlator which is associated to having these pairs in the quantum depletion. And so this is this guy that may build some new type of properties and some type of entanglement.
May I ask
Yes.
a quick question? Here you explained us that basically the Rayleigh entropy is some kind of merger of entanglement. Okay. And you have the Rayleigh entropy that goes from 0 to some finite value when you go from mod to superfluid. Right. That's what I understand from this graph. And then below you explain us that at the quantum phase transition, then you have a growth of entanglement, but then you should go back to some lower value.
So I said two things. The first one is this type of scaling. So this was done for Ising type of Hamiltonian.
Yes.
We are talking about another type of Hamiltonian here. And so it's not this such a statement that, let's say, correlations, many-body correlations and entanglement would be somehow maximum at the quantum phase transition. This is not universal
Okay, so
yet.
it's not true in the case of the...
So I don't know in the case of a mod transition whether it's true or not. The thing that and then the second statement is that, of course, the type of entanglement you will get depends a lot about the degree of freedom you are considering. So this is position space, and now I will tell you about momentum space. And in the momentum space, you get somehow, in the superfluid, a slightly different picture from position space. So then, for instance, I could, let's say, I may argue that in the momentum state, in the momentum space, for this mod transition, you may have actually an increase of correlation at the quantum phase transition. Okay, so let me tell you about a recent measurement we did to basically to be able to see those correlations. So I've already shown you that we have this three-dimensional detection of single atoms. And so what we can do, we go in the superfluid regime. This is why you have those diffraction peaks, which you see here. So this is a cut through the momentum distribution. Well, it's a semi-log because in linear scale you don't see the depletion. And now what I'm doing is I'm looking in this green area here and looking at this type of two-body correlator. And what is plotted here is this anomalous term, which is plotted as a function of k plus k prime. And you see that we see a bump at k plus k prime equals 0, which means at k primes equal minus k. So this is a signal that we have atom pairs in the quantum depletion. So I'm not showing all the detail, but we've shown that with temperature this goes away and it has the good properties one expects from Bogolyubov theory. So first of all, I mean, we do have those pairs in the depletion of an interacting Bose gas. And now, what kind of property does it give to the ground state? No? Yes? Okay. So the interesting part is typically to compare this type of, let's say, new correlation induced by interactions with what you have only from statistical properties. And so what is plotted here, it's, let's say, the comparison of the amplitude how strong these anomalous correlations are. So these are the green dots, compared to the blue dot, which is just the normal correlation. You see this N and A. And what you see is that we have anomalous correlation that largely exceed the local correlation, the normal correlation. And this strongly violates, so if you would have a state that follows Cauchy-Schwarz inequality, you should have this, that the anomalous correlation are always inferior less to the normal correlation. So this strongly violates Cauchy-Schwarz inequality, which means that you have non-classical correlations. Well, this is what Bogolyubov tells us, right, somehow. But now you can see it in the experiment. And what is interesting is that such a large deviation, if you, I mean, there are many papers from which you can actually relate this large deviation to the fact that the state is non-separable, that the state is entangled. So there is one thing to be able to really make such a statement from the experiment, is that we should look at the crossed first-order correlation between minus k and k, which we have not done yet in the experiment. So I'm not claiming in the experiment that this is a proof of entanglement, but let's say it's clear that it goes in this direction. And you see what is interesting is that you just take Bogolyubov picture, which is really simple. It's just like you treat interaction perturbatively. You get some new correlations. And actually, from this new correlation, you get some non-trivial properties also for the equilibrium state, for the new many-body ground state. So there is this link between correlations and entanglement, and how interactions and quantum fluctuation induce those, let's say, intricate properties. I think it's really like fascinating topic, and I hope we will learn more and more in the next in the years to come. And actually, it's fascinating both for experimentalists and theorists, because I mean, as you know, it's not we don't have a clear definition of what would be a many-body entangled state in any, I mean, in a universal way or whatever. Okay, so I think I will stop that. Yet I will skip the correlation in the mod state. Do you have questions?
Yes. Do people also try to measure something like this in a strongly correlated system?
In
a strongly correlated system?
So what are you referring to?
Like lithium-6 and BCS crossover?
Ah, with fermions.
Yeah, okay, that changes the whole.
Because so far I was talking about bosons.
Yeah, that's true. But with fermions, yes.
Well, not directly this type of stuff yet, but I will briefly mention some recent measurements. I mean, what people are now very much into with fermionic quantum gas microscope is to look at somehow magnetic correlations and all correlations. So typically, but I will tell you about that. So, but I mean, of course, with quantum gas microscope, people have been measuring, like over the past, let's say, 3-4 years, heavily correlations, both in spin and in density. And the interesting physics looks like when the two are kind of, let's say, playing both a role. And this I would like to illustrate in what is coming next. Yes.
Could you essentially measure the correlation with this entanglement measurement?
Alors, so well, we can measure some. Well, for instance, I mean, let me tell you. So this is a two-body correlator, and so this delta k is k minus k prime. Okay, so you can measure this two-body correlator as a function of the distance, and then you can, let's say, extract a width, which is, for instance, plotted here. So yes, you can. So this is a different stuff, but whatever you can. I mean, you know, if you have the three-dimensional position of your atom, or with a quantum gas microscope, you have the two-dimensional positions, then you can measure correlation as a function of the separation. And therefore, you can measure how the correlation function goes down and extract, so both amplitude and width. Okay, so let me now arrive to the fourth lecture. So we have a little bit of, we are a little bit delayed. And so what I would like to discuss now is the case of fermionic atoms. So I will not be so I have basically 1 hour to introduce a bit of a physics of with fermions in optical lattice. You will hear a lot, I guess, about some strongly related physics, the physics of spin systems during the week, and so that's why I am not spending too much time on this part. Okay, so well, we had the Bose-Bart Hamiltonian, so we can have now the Fermi-Bart Hamiltonian. So I will consider, as we did with the Bose-Bart Hamiltonian, the lowest band only. I am in a tight binding regime. So I will write the Hamiltonian in second quantization, exactly as we did with the bosons. But now, I mean, to have, you've seen with an Amari-array, for instance, that if you want to have interactions, you should have at least 2 fermions in the lattice. Because if you want to have, 2 identical fermions in the same lattice state in the lowest band of the optical lattice is forbidden by Pauli principle. So we will use, we will consider two states that I will label up and down. So for instance, 2 hyperfine states of a fermionic atom. And so the Fermi-Bart Hamiltonian, write this way. How did I? Yeah. So a kinetic term with so it's still next nearest nearest neighbor. Sorry, JJ prime. So T, the tunneling amplitude now has become small t. So this is because we are coming closer and closer to condensed matter, where they use small t for the tunneling amplitude, and you will introduce a j amplitude very soon, which has another meaning. But so this used to be I used to call it j for the bosons. And then I have an interaction term. Well, when I have the 2 atoms with opposite spin on the same site. And well, I can also have some on-site energy as well, if you wish. Okay, so this is just the analog, but now with two spin states of the Bose-Bart Hamiltonian. Well, so we can do exactly as we did with the Bose-Bart Hamiltonian to start with. So first I will consider homogeneous system, just to make my life easier. And so we have a situation where, let's say, you take a non-interacting system with some tunneling. So what would be the type of state that we will obtain? Well, it would be a metallic state. And the other extreme situation is if we take the tunneling towards 0, but have some on-site interaction. Well, we will get a Mod insulator with 1 atom located at each side of the lattice. So this is just analog somehow of the physics that we discussed with the bosons. And so this has been observed in experiment. So now so it was 2008. So this transition from a metal to a Mod insulator. And the way it was measured is depicted here on this diagram. So if you have no interactions, and now we are accounting for the fact that in the experiment you have a harmonic trap. So the atoms, they somehow accumulate here, so you never have 2 times the same color on the same site, of course, by Pauli principle, but we have doubly occupied site, okay? And the atoms are moving around, so interaction is 0, but T is non-zero. If now you go to the other regime, well, actually in this experiment, small t is still called J. So this is tunneling, this is temperature and chemical potential. So if you have a strongly interacting system, then you have the atoms, you will have only one atom per lattice site, and you will get an insulating state. And you see that from here to here, what changes drastically is the doubly occupancy. Of course, in the Mod state, you will not have doubly occupied site. And so this was what was measured in the experiment. You have the fraction of doubly occupied site, which is plotted here vertically. And you see that, so here it's a non-interacting system. U over 6j equals 0. Here it's interacting. And you see that there's a huge difference in doubly occupied site from one non-interacting system to a strongly interacting one. Okay, so this is a physics that one can obtain at strongly interacting systems, so fermionic Mod insulator, similarly to what we have discussed for the bosons. Well, similarly, actually, this is not true. Because for the bosons, we had only one color, one spin state. Here we have 2 of them. And so now, so we have this spin degree of freedom. And so if I wonder what is the ground state, well, let me do like this. So let's say that the ground state in the limit of the Mod insulator, right? Large on-site interactions. I know I have 1 atom per site. But of course, I mean, I can have, I don't know, up, 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 and down, down. But I can have any combination I want. Of these guys, right? So the difference with the bosons is that now the ground state is highly degenerate, well, to the power of a number of sites. So this changes a lot the physics, and I would like to to first say the following. So I have a highly degenerated ground state in the limit at least u equals 0. Let's say t equals 0. And now I ask the question, what happens if I start switching on tunneling? So there is one obvious thing that may happen. So if I consider small tunneling, but which is, let's say, positive, so still much smaller than u, what I can have is one spin, but of course tunnels to the next site. Okay? This would be like a first excitation on this ground state. So now if I want to, let's say, I will try to re-put exactly the same, so how was it? Like that, then, tuck, and tuck. So the energy difference between those two guys is, of course, the on-site interaction u that I must pay. And the coupling is the tunneling energy T, okay, to go from one side to the other. So if you use, once again, I mean, I think you have heard of it many times, second-order perturbation theory. Well, how will be the energy of a ground state modified to second order? Well, it's the coupling square divided by the energy gap. So you see that we have a new energy scale, T square over U, that comes into the problem. If you want to excite, let's say, from the ground state to just like move a spin from one side to the other. So this is this type of new energy scale is actually bringing this Fermi-Hubbard Hamiltonian to be mapped onto a spin Hamiltonian, in particular the Eisenberg Hamiltonian. And this energy scale will be called the super exchange energy. So I would like to just tell you a little bit how this works on a simple, just starting on a simple situation, which will be consisting in considering two lattice sites only. So I have these two sites. I will consider, so U much larger than T, positive, and I will consider what is called half filling. Half filling means that you have a total number of atoms, or spin, which is equal to the number of lattice sites. And I will also consider no doping. I will remove that. So no doping means that the number of spin up is equal to the number of spin down. And so therefore, each of them is equal to half the number of lattice sites. So in my situation, I have one spin up and one spin down. Okay. So the first thing is, which is easy to realize, is that if I, this will be lattice site 1, this will be lattice site 2. And I can write the total spin, which corresponds to that, which is the sum of the spin, total spin on lattice on site 1 and on site 2. And so this guy commute with the Hamiltonian. There is nothing which changes it. And so therefore, what I will be doing is considering only, to start with, spin singlet. Total spin S equals 0 states. So what do we have? Well, we have a state when I have up and down on site 1. We have a state where I have up and down on site 2. And then I can also, of course, have up and down, minus down, up, square root 2. Okay, these are free states with spin equals 0. And so I want to write the Hamiltonian in this sub-basis or spin s equals 0, and then we will do for s equal 1. So let me call that S. So this guy has 0 energy, this one interaction U, and this one interaction U. Then these two guys, they are not coupled. While, of course, I can tunnel from having up and down to both of the two. And so from this singlet, as I have 2 times this t over square root 2, which is square root t, square root 2 times t, square root 2 times t, and it's the same, of course, for this guy. Yes? Okay? And so now, well, this is something that you know how to solve. And the eigenenergies in the limit u much larger than t, so I do the calculation in perturbation, so what? No. Great. So what do I get? I get u plus 40 square over u, and u minus 40 square. No, I get 0. Yes, u minus 40 square. No, I think I did something wrong. Yes. So the eigenenergy has I have u plus minus 40 square plus u over 4. And so with a minus, the u goes away, yes. So 40 square divided by u. Okay, so these are the 3 eigenenergies. So I can do exactly the same for s equal 1. And what I find is that I have threefold degenerate state, which they are all the same eigenenergy, which is nil. I'm not doing all the calculation. Okay, and so now what I would like is just to draw the energies we have. So at 0, we have total spin s equal 1, so it is 3 times. Yes, and then so I have one state which is minus 4t square over u. And then I have u and u plus 4t square over u, so two other states here. Okay, so I have solved this simple two-site model. And so you see that this is what Anna Maria said, is that we favor the state to go towards the singlet state, and therefore to have an antiferromagnet. And so what is this 4t square over u? Well, the physical way of seeing it is that you will have, I mean, it couples these two guys together, of course. And so this is called the exchange energy. And this is somehow, you can see it as also as going, so it's second order perturbation theory if you wish, or if you wish is going up to a virtual transition to the state where you put these two guys together, it's lifted up by the on-site interaction energy U, and then you tunnel the other direction. So okay, and so this new energy scale and the fact of like changing the spin actually is similar to what happens in several types of solids, where you do not have direct spin interactions, but so let's say from these two guys, they don't interact together directly, but you have this spin exchange interaction, which consists in flipping the two spins from adjacent sites. And so this is similar to this type of physics. And actually, you see that if you wish to rewrite the Hamiltonian, which is associated to this type of term, then what we are doing is flipping. So let's say that if I go, if I flip from mine on the site, no, sorry, this will be on the site 1, I flip the spin S minus, on the site 2 S plus, and I end up in this state with some kind of amplitude. And of course, you can do which can also be rewritten as S1x S2x plus S1 epsilon S2 epsilon, where S, well, it's just the usual. So Sx J is S plus plus S minus divided by 2, and S while divided by 2i. So why am I doing that? Well, it's because I've already kind of anticipated that I would go towards the Eisenberg Hamiltonian. So you see that this exchange term gives me SX plus SY. So to get the Eisenberg Hamiltonian, I'm only missing S zeta, which you actually get from the part which is, so yeah, I will not do it, but for the part which is spin conserving, you also can write a term which is S zeta. So I'm not detailing it. And so in the end, your Fermi-Hubbard Hamiltonian, so which is in the limit u much larger than t, no doping, and half filling. So with these three conditions, your Fermi-Hubbard Hamiltonian can be mapped onto Eisenberg, which is well, S1, S2 in the case of my two sites, and therefore for the Fermi-Hubbard, it's just like a J prime, S J prime. Well, this is just like going a bit fast, but just to give you the flavor how you do that. And remember the conditions. It's like you are considering, basically, you are in the Mod Insulator regime. You have no doping and half filling. So one atom, well, the number of atoms is equal to the number of sites. Okay. So what do we have? For the 3D Eisenberg model, we have a phase transition at a temperature which is the Néel temperature, which is proportional to this exchange term. And what is the phase transition? Well, it's a phase transition from, if you are at 0 temperature, you essentially have an antiferromagnet, right, which is the one which will lower your energy. And if you are above this Néel temperature, then this magnetic ordering is completely smeared out by all the thermal fluctuations. Okay, so that's why this temperature is also typically associated to this energy scale of the superexchange interactions. And so this was observed in experiment a few years ago. And I would like to tell you a little bit about it. So actually, before going to this type of observation, let me tell you that first, 2015 was the year where quantum microscope for fermions appeared. And actually all those groups published the same year this observation of, so you see, it's as with a boson, you see this single atom on single sites. So there are two species, potassium-40 and lithium-6, which one has managed to see under this type of microscopes. So it's, well, it's 6 years old, so it's not that far. Well, okay, I will not detail that, but one reason, so remember the boson, the quantum gas microscope with Bose gases was working from 2009. Okay, so 6 years earlier. So why did we, and so actually all these experiments, they already started the fermionic one soon after obtaining the bosonic one. And so the reason why it took like kind of long, like 6 years, is because in these two fermionic species, lithium-6, well, especially potassium-40, you have hyperfine levels which are very close to each other. And so it's not a good situation to have efficient laser cooling by molasses. So, and you remember, you need to hold the atoms for typically like a second or so to be able to see enough fluorescence. And so you need to cool them down. And so this was not the usual simpler schemes, were not efficient in that case. And so they went to EIT cooling. And lithium-6, lithium-6, it's really light. So it's easy to give it some recoil and have the atoms fly away from the trap because their recoil energy is large. And so they used Raman sideband cooling. So I mean, these teams needed to develop a bit more elaborated cooling techniques than the ones were used with, let's say, the rubidium quantum gas microscope. But they managed. And so let me just first show you the observation of a Mod Insulator under the microscope, which I think it's really fascinating. So this is this part here, this column here on the right-hand side. You see the lattice site, you see the atoms, and you see that you have almost like a perfectly filled Mod Insulator. So well, of course, I mean, you have a few defects. It's not strictly zero entropy state, but it's incredibly nice. And of course, you can also observe the metallic state. And so this is the observation of the metal to Mod Insulator transition. So this was 2016 in Harvard. And why did I? Yes, okay. And so now I was talking about this Eisenberg Hamiltonian in this U of a much larger than T limit, no doping, half filling. This is like a let's say, phase diagram, which it's a bit more accurate than what I've been deriving, but typically you recognize the Mod Insulator. So large U over T, it's with repulsive interaction. Sorry, I didn't mention it. I was considering repulsive interaction, of course. U much larger than T, it's in this regime, and so you see that you have the Mod to antiferromagnet phase transition. And then you have also interesting things appearing on the attractive part. I will not have time to tell you. So all this is half filling. Right? Keep in mind that. Number of atoms equal number of sites. So, and in Harvard, they were able to see this phase transition. So this is a phase diagram. You have temperature there. This is doping. But so I told you I am at half filling, so I'm only considering zero doping for the moment, so I'm there. And you have here a picture in the antiferromagnetic state where on top you have the fluorescence from both up and down spins. So you see that almost all lattice sites are occupied, except a few here. And this is fluorescence on only the spin up. And you see that you observe this checkerboard pattern, which is, of course, due to this antiferromagnetism. So one of the big issue, I mean, to obtain these results was, of course, to lower the temperature, because you need to be on this type of scale. But I remind you that we are talking about the regime. We start from a Mod Insulator. So U is much larger than T, and this is T squared over U. So it's very small, which means you really need to lower the temperature. And one of the trick that they used in this paper was to actually engineer some different trapping potential with like different density of states. So very shallow trap with like a lot of states on the edge, and like a steeper trap with just a few states at the center. And so therefore they could put all the finite entropy that you always have in the experiment, they could put it mostly on the side here. in what they call the reservoir. So ending up with a central part here, which was effectively a low entropy one. And so at an effective temperature, which could be lower than this exchange temperature. So you see, this is a picture of the entire system, and this part here corresponds only to this inner circle there. Okay. And what you typically want to measure in this type of systems in order to go towards like quantifying correlations and, for instance, measuring correlation length is to look at this staggered magnetization, which in 1D is kind of simple. So we can have spin up, spin down, okay? And so if you have antiferromagnetic order, you have up, down, up, down, up, down. And so what you do is you measure the projection of the spin on each side, and then you add a -1 each odd side. So if it is perfectly antiferromagnetic, this will come to summing up all the contributions. Okay? So you have, so this is a -1, like in staggered magnetization in 3D. But if you are in 1D, so this is the experimental measurement, it's -1, for instance, to the power of the number of the site. And so this is the measurement of the staggered magnetization, so in blue, as a function of temperature in unit of the tunneling. And so one sees that indeed you have staggered magnetization that increases, which, from which you can quantify the antiferromagnetic order. And they also measured the length over which you would have this antiferromagnetic order. Okay, so this was at half filling. And let me stress one thing. You see that you have a theoretical curve here from quantum Monte Carlo calculation. Half filling means, once again, you have one spin per site. But you see, if I now look, so we've been discussing this part only. If I now look at this phase diagram, which is inspired from ITC superconductors, actually cup rates. Well, people know that there is a transition from a Mod insulator to an antiferromagnet. This is well known, and one also can perform numerical calculations. What is an open question is what happens when you move in this direction, which means you start doping the system. So doping the system in such a cold atom experiment means you either put a little bit more of atoms than the number of sites, or you put some holes. You just remove a few atoms. And all this part of the phase diagram, I mean, there are some, of course, as you know, experimental observation, for instance, of the fact that you have D-wave superconductivity in cup rates. But we don't have an explanation for this type of superconductivity, and we don't know how to explain and even sketch such a phase diagram. So this is really an open question which is extremely interesting. And so they did some experiments by doping the system and measuring this staggered magnetization. Okay, so moving in this direction here. So since this school is called quantum simulation, I mean this is a real nice quantum simulation because we still, I mean, it's 2017. To my knowledge, there are still no calculation that can reproduce the experimental, this experimental investigation. The reason why it's so difficult is because of the so-called sign problem and of these fermions, right? So you have many fermions. You can have a spin up and spin down. So they would change the sign, of course, and the symmetry of your wave function. And the issue is that you have many spin up, many spin downs, and you need to therefore evaluate what is the difference. And the difference can be a tiny number, while you have like two kind of huge sums for the spin up and for the spin down. And so if you flip only a few, you may have a strong fluctuation on the numerics. While this does not happen at zero doping because you have a perfect symmetry on which that you can use for the numerics. I'm not an expert of these questions, but this is what I got. Okay. So, well, let me also comment on the fact that, as you see, the way they depicted this phase diagram and where their experiment was lying makes it clear that they could reach the Nel transition, obtain an antiferromagnet, but actually compared to a solid-state system, in terms of difference, the temperature in the experiment with respect with the Nel temperature is not that far. So in condensed matter experiment, they really go like to 1/10 or even less of the Nel temperature, while here it's, in this first experiment, it was just below the Nel temperature. And so in this region here, which is there, well, there are open questions with this pseudo gap phase and so on, but people are thinking that there will no observation yet of like superconducting state, because to do that, we would need to even lower the temperature. Okay, so this is like a phase diagram of this kind of doped insulators, and this is the type of phase diagram that we are sketching now, but we don't know exactly whether it is correct or not. What is clear from condensed matter is that so you see, increasing the particle or increasing the number of hole, you don't have the same phase diagram. So this particle hole symmetry is not there anymore. And we don't know how to describe those different phases. I mean, what kind of model we could use to explain these different observations. And so one of the model which is thought as a possible minimal model is this Fermi-Hubbard model. So that's why there is all this, let's say, work to study the Fermi-Hubbard model with, let's say, in the regime of strong interactions. So doped, Mod insulators, and then you add some holes or some particles, you doped it, and then one wishes to be able to see this type of physics. And so over the past years, there have been many, a lot of beautiful experiments in that direction. And one of the, what people are really studying now is, so doped systems. So we put some holes, typically. And the question is, what type of spin correlations do we get? So it's not a perfect antiferromagnet, okay? So what, how the presence of a hole will modify the magnetic environment. How a hole can move around, because then you have to spin the flips. And so therefore, it's very much about understanding the link between spin and charge transport, and how magnetization and transport are, let's say, working together in such type of systems. Okay, and actually there's also some, for example, experiment in Princeton where also this kind of, let's say, pseudo gap and strange metal phase have been studied. Well, there are many interesting physics in this direction. Okay, I think this is what I wanted to say about this Fermi-Hubbard. So basically, I just wanted to tell you about this limit, U much larger than T, where you enter the system can be described as Eisenberg Hamiltonian if you have no doping, and then when you have, if you start to dope the system, you have all these open questions, which for which we can hope that our atomic quantum simulators will be able to provide some new insights. So do you have any common questions about this? No, it's fine? Yes?
Is it obvious that you break particle symmetry in the Fermi?
No.
You don't, right?
Well, not to my knowledge, yes. But I mean, these are experiments. I mean, well, it's a phase diagram from experiments, if you wish. I mean.
No, but I saw the Fermi-Hubbard itself was not sufficient to explain the asymmetry.
Yes, I don't think so as well. But I mean, already understanding whether you have some pseudo gap, whether you have some superconducting states.
Yeah, so this is a phase diagram for Coulom's map, not for the Fermi above.
No. No other questions? Okay, so this is what we have been discussing together, right? A bit of optical lattice, band structure, interacting bosons, and like slightly touch about interacting fermions and how, let's say, magnetism can come up in this Fermi abart. And so if you have no further question, then I wanted to leave you with this picture. So we've talked about the first Brillouin zone. So this is like the three-dimensional version that you can measure with a three-dimensional detector using this band mapping technique that we have discussed together. And with that, I thank you for your attention.
Sure, no questions?